Start. Okay. Hello and good evening everyone. Today we are going to start a new unit, coordination compounds, a very important unit, and there is a continuity for this unit. Coordination chemistry, we will be learning all the basics, but in your syllabus for coordination chemistry, they have started from IUPAC nomenclature directly. Then they have entered into some theories. But before directly going into IUPAC nomenclature, let us discuss some basics also. What are the different types of ligands? How do we classify all these ligands? So we will be going through some basics, then we will be entering into your topic. So put the main heading as coordination compounds. A very important unit, coordination compounds. So we will just begin with the basics today. We'll just take all the basics, then we'll slowly move to the main concept. We are aware of what are ions. Ions are charged species. There are two different types of ions. One we call it as a cation, the another we call it as a anion. A positively charged species we call it as a cation. Negatively charged species is called as anion. But again, this cation can be further classified into homoatomic and polyatomic. We can further classify these cations into homoatomic and polyatomic. Please make a correction, monoatomic. Monoatomic and polyatomic. Likewise, even for an anion, monoatomic and polyatomic. Monoatomic, any example for a cation? Many, but just we'll take one or two examples. Sodium or potassium and so on. For polyatomic, we again have two types, homopolyatomic and heteropolyatomic. For homopolyatomic, you can take an example of Hg2 2+, two metals are one and the same, mercury. If it is a heteropolyatomic, I can choose some interhalogen compounds, ClF2+ or ICl2+ and so on. Likewise, for anion also, I may choose a halide. I can choose a halide which is a monoatomic. If it is polyatomic, again we can classify into homopolyatomic and heteropolyatomic. Homopolyatomic, two atoms must be the same. I can take O2 minus, I can take O2 2 minus and so on. Or I may take N5 minus pentazenium. N5 minus is called as N5 plus or N5 minus. Here N5 plus you can take. N5 plus we'll take there. Here I can give you N3 minus. Homopolyatomic. All the three are nitrogens. For heteropolyatomic, any example? Plenty. You just take SCN minus, OCN minus, etc. They are heteropolyatomic, cyanato, isocyanato, thiosulfato, thiosulfato S, thiosulfato N. We will be seeing different types of ligands. So what are the different types of ions means we are aware of. Basically there are two ions, cation and an anion. Cation is a positively charged species, anion is a negatively charged species. Cations or anions are further classified into monoatomic and polyatomic. Monoatomic means a single and polyatomic means more than one. Within polyatomic we have homoatomic and heteroatomic. Homo means same number of same identical atom. Hetero means different atoms will be present within the ion. This is just a basic classification of cation and anion. Have you taken it? Suppose I take a simple cation and a simple anion. Let me take a simple cation and a simple anion. Whatever you get is a salt. We simply call it as a salt. So what is a salt means it is the combination of a cation and an anion. You can call it as a simple salt. I am just calling it as a simple salt. Now let me take another simple salt, potassium sulfate. I am taking aluminum sulfate. Whenever I take a simple salt, I just dissolve it in a suitable solvent. Say I am dissolving it into water. Once I dissolve it into water, that simple salt will be ionizing into corresponding cation and corresponding anion. Na plus and Cl minus will come out. But suppose if I am taking two such simple salts, and then I will be just combining them. How do we combine? I take two different simple salts. I will take a suitable solvent. I will dissolve in it. Once it is dissolved, I will again evaporate. Once I evaporate, I will be getting a compound. What do those compounds called as? Suppose I have taken this. I have taken one more salt. I am taking one more salt. This will give you some product. This will also give you some product. So those products we call them as addition compounds. Addition compounds. So what are addition compounds? When I am combining two simple salts, that will give you some compounds. These compounds we are calling them as addition compounds. I'll just give you the points about the definitions. These classifications you can note down. So these addition compounds are of two types. One we call it as a double salt. The another is called as a complex compound. Okay. Now let us understand what is a complex compound. Suppose I am taking two simple salts. I am dissolving it into a suitable solvent. Later on I am just evaporating the solvent. Once I evaporate the solvent, whatever I get, that I may call it as a double salt or I can call it as a complex compound. But whatever compound that I got, I again redissolve into the solvent. Once I redissolve into the solvent, if I get the corresponding cations and anions again, then we call it as a double salt. I am just repeating this point again. I have taken these two simple salts. I will be getting a product. That product is called as what is that salt called as? Potash alum. We call it as potash alum. So if I am putting potassium sulfate and aluminum sulfate in water, I will be getting some compound. That compound is called as potash alum. Whatever compound that I get, when I again redissolve it into the water, whenever I am redissolving into water, I will be getting the corresponding cations as well as anions. It means I will be getting potassium separately, 2 potassiums, 2 aluminiums and also 4 sulfates. So if you get all the corresponding cations and anions, such an addition compound, you call it as double salt. But on contrary, I have taken AgCN and KCN. So when I take AgCN and KCN, I dissolve, both are two simple salts. But whenever I am taking the product, I dissolve it into water again. When I dissolve into water, I am not getting all the corresponding cations and anions. Instead, I will be getting only two ions, one cation, one anion. Now what is the definition of a complex compound means? If I am dissolving a compound into a suitable solvent and if I am not getting all the corresponding ions, such an addition compound we call it as a complex compound. So two simple salts I take, I dissolve into water, I then evaporate the solvent completely. Then suppose if I redissolve the salt or the addition compound, if you get all the corresponding or constituent ions, you call it as a double salt. But if you are not getting all the constituent ions, you can call it as a complex compound. Write down the definitions for these two. Wherever necessary, I'll dictate all these definitions. Double salt. Double salt is an addition compound. Double salt is an addition compound double salt is an addition compound which produces all the constituent ions when dissolved in the suitable solvent. Definition. Complex compound. It is an addition compound which when dissolved in a suitable solvent does not provide all the constituent ions. Example, you have taken AGC an example? Okay, you can just write down that example. When you dissolve it into solvent, you will be getting only 2 ions. But you will not get K, you will not get Ag, you will not get 2 cyanides. 4 ions will not come, only 2 ions are coming. How do you identify whether the complex compound has formed or not? There are different evidences. Suppose I can take conductivity measurement. This is one of the important parameters through which I can understand whether the complex compound has formed or not. Suppose if I am taking a double salt, I just dissolve it into a solvent, I will get all the constituent ions, the conductivity will increase a lot. But if I am taking a complex compound, I dissolve it into a suitable solvent, I will not be getting all the constituent ions. The number of ions that we get is less. So what will happen to conductivity? Conductivity, whatever is expected, will drop. So conductivity measurements is one of the best parameters to understand whether a complex compound has formed or not. That is one way. There is also a second parameter. What is it? Solubility. Whether complex compound has formed or not, solubility will also help us. As we go into the main topic, we will be knowing it, how solubility will help us. Solubility or precipitations and so on. Also, color and magnetic properties will help us to understand about the formation of a complex compound. Color means simply if I take copper sulfate, pentahydrate, I am adding ammonia to it, you will be getting tetramine copper sulfate. What is the color of copper sulfate? It is sky blue, light blue. I am just writing it as light blue. But once it is forming a complex, suddenly the color will change. The color will be intense blue. The color will be intense blue, a little indigo kind of a color, not purely indigo, but blue with indigo kind of a color. So even if there is a change in the color, or there could be change in the magnetic properties, or conductivity, or solubility, all these parameters will help us to understand whether the complex compound has formed or not. You can just write down these parameters. With respect to double salt, conductivity measurements will drop. Now just let me take a couple of examples of complex compounds. Finish these parameters. Whatever complex compound that I take, we have a simple definitions of the corresponding terms. Suppose I am taking whatever ion that is present outside this box. What do you call this as? We generally call them as brackets. But these are called as square brackets. There is a differentiation. Suppose if I put this, we have to call it as parenthesis. These are called as braces. And these are called as square brackets. So whenever I am representing a coordination compounds, we have to always use a square bracket only. Within the square brackets, whatever you are putting, that we call it as a coordination sphere. All this is called as a coordination sphere. And whatever is present outside, that is coming under ionization sphere. For some, ionization sphere will not exist. So this comes under coordination sphere, this comes under ionization sphere. Let it be a cation, let it be a anion. Within the coordination sphere, you will have a central metal. It could be central metal atom or it could be ion, depending on the oxidation state of the central metal. So I can call it as a central metal atom or a central metal ion. Whatever that are surrounding this cobalt, which are binding to the cobalt, we call them as ligands. In this case, cyanide is a ligand. Amine is a ligand. Chlorine is a ligand. But this chlorine, you should not call it as a ligand. It is called as a counter ion. This is a counter ion. Okay? Suppose if I am taking this coordination sphere, this coordination sphere is cationic. This is having a positive charge. Whereas this is a negatively charged species. If I don't write this Cl2, what I get is 2+. So this we call it as a complex cation. If this is a complex cation, what is existing is a anion. So we simply call them as counter ions. For my complex cation, the counter ion is anion. In this case, for my complex anion, the counter ion is a cation. So whatever is existing outside, that is called as a counter ion. That could be counter cation or counter anion. You can directly write it. Atoms or groups existing outside, atoms or groups existing outside the coordination sphere, are called as counter ions. It could be a counter cation. It could be a counter cation and a counter anion. It could be a counter cation or a counter anion. Sometimes hydrated water could also be present. Sometimes you find water molecules also outside. I cannot call it as a counter ion. It is not an ion. Ion means definitely it should have some charge. Either it could be a counter cation or it could be a counter anion. Water you should not consider as an ion because it is neutral. Okay, now I'll just take a few classifications. How do we classify all these complex compounds in different ways? First type of classification, This is based on charge of the complex. How do you classify based on the charge? How do you classify based on ligands? How do you classify based on metals? All classifications will take. Directly I'll write cationic complex, neutral complex, anionic complex. Cationic complex, cobalt complexes were the most studied complexes because they are found to be inert complexes. They are found to be inert. Therefore, they have studied cobalt complexes a lot. So, very frequently we give example of cobalt. Cationic complex means it is a complex where the charge is positive. Here the charge is negative. You may write it as +2, -4 also, it is up to you, but according to IUPAC convention, always the number must be mentioned first followed by charge, not charge followed by number. We generally put +2. Suppose if I write some complex, I write +2. But according to IUPAC, 2 plus is correct. Even if you put +2, that is fine, we can understand, but 2 plus is more correct. Just like you call fluoro, chloro, it is right, but fluorido, chlorido is more correct. Just a small difference. So based on the charge of the complex, I can classify them into 3 types. One we call it as cationic complex, neutral complex and anionic complex. In neutral complex, there is no charge, but oxidation state can be same. So please make a differentiation between oxidation state and charge on the complex. In this case, the charge on the complex is 2 plus. In this case, the charge on the complex is 0. But oxidation state is remaining the same. So oxidation state has nothing to do directly with respect to the charge on the complex. With the help of charge, you can calculate oxidation state, but there is no direct relation. Okay? Next one. Based on number of metals. I can classify based on number of metals into 2 types. One we call it as mononuclear complex, another is called as a polynuclear. Mono means a single metal atom, poly means more than one. It could be 2, it could be 3, it could be 4 and so on. Mononuclear complex, whatever examples previously I have given you, or else you can just take a new example, wherever you find just a single metal atom. Polynuclear complex, I can simply take Fe3CO12, where there is more than one metal, or now this is a bridging complex where you find more than one metal. There is more than one metal. 1 cobalt, 2 cobalt. Oxidation state, what is the oxidation state of the metal? Oxidation state, this is -1, -1, -1, -1. If I don't put these 2 chlorines, it is 2 plus. So 4 negatives, 2x minus 4, because we have 2 metals, so 2x minus 4 is equal to +2. 2x equals 6, x equals 3. Each metal is present in +3 oxidation state. Cobalt is stable in +3 oxidation state. So they are called as polynuclear complexes. What is a polynuclear complex? Nucleus is related to metal. Mononuclear means one metal, polynuclear means more than one metal. Mononuclear and polynuclear. Most of the metal complexes we take mononuclear. Polynuclear are very less. You get more number of polynuclear, but in organometallic chemistry, when you go to organometallic chemistry, metal clusters, they are polynuclear. You have more than one metal. Finished? Classification? Next one, based on reactivity also we can classify the complexes. Complexes are classified into labile and inert complexes. Two important concepts with respect to reaction mechanism, thermodynamics and kinetics. Thermodynamics is always related to stability and instability, whereas kinetics is related to the speed of the reaction. Suppose if the reaction is occurring, product has formed. Let the product be stable or unstable. But what is the time of the reaction? Did it take 1 minute or is it taking 1 hour? So you might be getting the same product, but time might be high. So kinetics and thermodynamics you directly cannot relate. Okay? Just suppose coming to this classroom you are becoming stable. Just imagine. But you might be catching a flight, you might be catching a train, you might be coming on foot. You are taking different times. So timing is different, but destiny is the same. You are attaining the same stability, but timing is changing. So that timing is kinetics, that stability is thermodynamics. Here I am speaking about inertness and lability. So this is related to kinetics only. Whichever complex reacts at a very faster rate, we call it as a labile complex. This will come across in reaction mechanism. Don't bother. This will come across in reaction mechanism. There we have to separately discuss. Just I am classifying them on the basis of reactivity. One we call it as a labile complex. An example you can take. A simple way to remember is all outer orbital complexes are labile. Whatever outer orbital octahedral complexes you choose, they will be labile only. In the inner orbital complexes, D0, 1, 2 are labile, remaining configurations will be inert. So cobalt is present in +3, 3d6, T2g6, Eg0. It is an inner orbital complex. So inner orbital complex could be labile or inert, but only D0, 1, 2 are labile. Any remaining configuration which is inner orbital complex is inert. Details will come across in reaction mechanism, so don't bother. Finish this classification. This is based on reactivity. Based on ligands, we'll write. Complexes can be classified into two types based on the ligands. One you call it as homoleptic, another we call it as heteroleptic. Homoleptic means just with the example you can understand. Lepton is related to ligand. If you find all identical ligands in a complex, you call it as homoleptic. Homo means all ligands are same. I may choose FeCN6 3-. All ligands are same. It is a homoleptic complex. But if the ligands are different, we call it as heteroleptic. It could be CONS3 taken 5 times Cl2+, or it could be some other complex where the ligands must be different. So such different ligands you call them as heteroleptic. Same or identical ligands, whatever be the number, that you call it as homoleptic. That is based on the ligand classification. Finished? Now we'll take combination. Based on metal as well as ligand, we classify the complexes into binary complexes, ternary complexes, ternary or tertiary, quaternary complexes. What is a binary complex? Now here I am considering both metal as well as ligand. In the previous case, when I classified on the basis of ligand, if you find only identical ligand of only one type, you call it as homoleptic, all identical ligands. Heteroleptic, different types of ligands. Here binary complex means, suppose I am writing Fe, I am taking CN6. This is a binary complex. Binary complex means one metal and only one type of ligand. So altogether there are two, one metal, one type of ligand. Such a complex you are calling it as a binary complex. You simply call it as a binary complex. Or I may take cadmium amine, tetrahedral complex. This is also a binary complex. What is a ternary? Ternary means three, one metal, two different types of ligands. Same examples repeat, but we are classifying on different ways. Here one metal plus two different types of ligands. So 1 plus 2, ternary. Ternary or tertiary is related to 3. Binary is related to 2. Quaternary is related to 4. So what could be an example? One, three different types of ligands. So 1 plus 2 plus 3 plus 4. Quaternary. Binary complexes are, binary and ternary complexes are more common, but quaternary or quinternary, they are very less. You need not go to quinternary, that is 5. 5 also you will find examples. Whenever we are working out the IUPAC names, we'll come across. But most common are binary and ternary. Above ternary you have quaternary and quinternary. Finished? So these are different types of classifications. Let us start with a metal. A metal surrounded by the ligands. A metal surrounded by the ligands, that we call it as a coordination sphere. So this is a coordination sphere, the primary one, the first one. In that coordination sphere, you can again have two different types. Two different types means, suppose if the ligands are simple atoms, imagine if they are simple atoms, chloro, bromo, iodo. If it is a simple atom, you can just call it as a coordination sphere, a primary coordination sphere. You can call it as a primary coordination sphere. But suppose if the ligand is a long chain one, imagine it is a long chain. Maybe I take acetate, right? Acetate monodentate, if I take. Or I may take some other ligand which has a chain. Maybe I'll take ethylamine. So if I take ethylamine, this is nitrogen, there is a chain for it. So this chain again will form another sphere. This chain will also form another sphere around the central metal atom. That chain you call it as a secondary coordination sphere. So whenever if it is a single atom, you call it as a primary coordination sphere, or simply you can call it as a coordination sphere. But if the ligand itself is a group which is having a chain, then that chain will also surround the metal atom. That you call it as a secondary coordination sphere. Primary and secondary coordination sphere. Suppose that the metal atom, I am taking this example. There are ligands and also there are some counter ions. So whichever counter ion that is present, let it be a counter anion or let it be a counter cation. These cation or anion, they also surround the metal, but from outside. That sphere you call it as ionization sphere. So first of all you have a coordination sphere. Coordination sphere could be primary or it could be a secondary coordination sphere. Apart from a coordination sphere, you also have a ionization sphere. Some complexes will have ionization sphere, some complexes do not have. It is not a compulsion. Some have, some do not have. Suppose if I take such a complex, I put it into a solvent. Whenever I put it into a solvent, those solvent molecules will come and surround the metal complex. So that third sphere, you can call it as solvent sphere. Whenever you are putting into solvent, definitely the solvent molecules will come and coordinate to the metal. That is not direct coordination. Simply call it as a solvent sphere. We call it as solvation. Solvation will occur. Right? So if I choose any complex, definitely there is one sphere called as coordination sphere. Ionization sphere, it is a choice. Only if it has a counter cation or anion, you can have a ionization sphere. Solvent sphere, it is again a choice. If you put it into a solvent, only then there will be a solvation. Then the third sphere will come. So if I speak about spheres, how many different types of spheres are present means there are 3 altogether. All the 3 may or may not be present. But altogether we have 3 spheres. Coordination sphere, ionization sphere, third one is solvent sphere. Coordination sphere can again be classified into primary and secondary depending on the type of the ligand. If the ligand is a simple atom or a simple group, you will not have any long side chain. Suppose if I take a CO, carbonyl, it will not have a long side chain, simply carbon and oxygen. So you need not expect a secondary coordination sphere. You can just consider it as a primary coordination sphere only. But if it is a lengthy chain, then it can act as a secondary coordination sphere. So when I say secondary coordination sphere, that chain is not coordinating with the metal. It is just surrounding. That's it. It is not coordinating, but still we call it as a coordination sphere because somehow it is directly attached to the metal. Okay? It is attached to the metal only. Donor and a continuation. Finished? These are different types of spheres. Primary, secondary coordination sphere, ionization sphere, and solvent sphere. Just add a point there. Ionization sphere is a choice. Ionization sphere is a choice of the complex. Ionization sphere is a choice of the complex. Next, solvent sphere. Solvent sphere appears due to solvation. Solvent sphere appears due to solvation. So only when you put it into some solvent, a solvent sphere will be there, or else there is no solvent sphere. Next, small subheading. Small subheading. Coordination number. Because in some questions they will give you a complex and they may ask you what is the coordination number and oxidation state of the central metal atom or the central metal ion. So how do you define a coordination number? Suppose if I am taking any complex. Imagine I am taking a complex. So prior to this, I'll write it here. Some metal, many metals can combine with EDTA. Now if I ask you what is the coordination number, coordination number is not the ligands that are present in the complex. It is not the ligands which are present in the coordination sphere. Because if I say that coordination number is 6, coordination number is 3, coordination number is 1, we are wrong. Then what is coordination number? It is the number of sigma bonds that are formed between the metal and the ligands which are present. It is the number of sigma bonds. So in this case, how many number of sigma bonds are there? 6. Therefore, coordination number is 6. So you have to just count the number of sigma bonds. There could be pi bond also. If at all there are some pi acceptor ligands, or if there are any pi bases, pi bond is also present. But you have to consider only sigma. Okay. Now suppose let me take COEN thrice. What is the coordination number? So what are the sigma bonds? 1, 2, 3, 4, 5, 6. There are 6 sigma bonds again. Though there are only 3 ligands, but the number of sigma bonds are 6. Therefore, coordination number is again 6. Suppose if I take metal EDTA, what is the coordination number? Generally, it is expected to be how much? 7. No? Now, how many bonds are present around the metal only you count? How many? 1, 2, 3, 4, 5, 6. So again the coordination number is 6. I am taking 3 different complexes. But in all the complexes, the number of sigma bonds is only 6. Therefore, coordination number we call it as 6. So what is coordination number means? It is the number of sigma bonds that are present around the metal. Okay, write down the point, coordination number. You can note down the examples later, you just write down the definition. Coordination number, it is defined as the number of sigma bonds. It is defined as the number of sigma bonds surrounding the metal. Number of sigma bonds surrounding the metal, or it is the number of donor atoms. It is the number of donor atoms of all the ligands put together. It is the number of donor atoms of all the ligands put together. Put together. Now you can just draw those diagrams. One is simple monodentate ligands, another one polydentate, one is polydentate, bidentate, last one is a polydentate hexadentate ligand. EDTA, the last one, it is tetraacetato, ethylene diamine tetraacetato. So there are 2 nitrogens along with 4 acetate groups. Acetate groups are CS2COO. So whatever ligand that you take, you are just taking it as nitrogen. For 2 nitrogens, there are 2 acetates. So CH2COO, 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 CH2COO. It will form an octahedral complex. It is forming an octahedral complex. most important one in coordination chemistry, ligand. It is as important as metal. Finished? Okay, come to ligand then. Write the subheading as ligand. What is a ligand? Ligand is any atom or a group which has the capacity to bind with the metal. As simple as that. Okay, write down the definition. Ligand is an atom. Ligand is an atom or a group. Ligand is an atom or a group which has a potential to bind with the metal, which has the potential to bind with the metal. It may form a sigma bond, it may form a pi bond, but still it is binding with the metal. So there is some other definition. What is the definition? Ligand is something which will donate its pair of electron. That is a simple definition. Because ligands donate, but ligands also accept. Ligands may also accept. So that definition is not correct. Because there are some ligands, I take CO. CO is donating, it is also accepting. So that is not a fullest definition. Simple definition is ligand means it is any atom or a group. It could be an atom or a group which has the capacity to bind with the metal. So where do the word come from? Ligand means ligaire. Ligaire means to bind. This was the word given by Alfred Stock. In boranes, he has done a lot of things. Alfred Stock. Borane chemistry, you will be finding the name of this scientist. Okay. Next, we'll go to classification of ligands. Once we go to classification of ligands, we'll take a few ligands which will very commonly occur in our complexes. Classification of ligands. First classification based on strength. All this is like revision, and I am giving you the full basics because directly I cannot jump into IUPAC without knowing all these things. Most of you might be aware of all these basics, but for those who find difficulty, we have to start with some basics. Therefore, I am starting all these things. So ligands can be classified into three different types based on the strength. One could be a weak ligand, one could be a moderate ligand, one could be a strong ligand. Examples I am not giving because there will be plenty of examples for each and every classification we cannot give. This you can understand. Weak, moderate and strong. Suppose if I have to give any example for moderate, which example can you give? Weak is known, halides. Halides are weaker. Strong is known, any pi acceptors. Pi acceptor ligands are stronger. Carbonyl, nitrosyl, phosphines, all those are stronger. Weaker are halides or aqua and so on. Moderate, nitrogen containing ligands. Amine or pyridine or ethylene diamine and so on. So slowly it will be moderate to strong. They will be from moderate towards strong. So as I move from amine, pyridine, ethylene diamine, phenanthroline, they are slowly becoming stronger, but they are not fully stronger. They are moderate to strong. So that is how we can classify based on their strength. Finished? Next classification based on orbital overlapping interactions. Based on orbital overlapping interactions, we have three different types of ligands. One we call it as a sigma base. Sigma base means, in a simple diagram I am giving you, suppose if this is a metal, this is a ligand, that ligand is donating a pair of electron. All such ligands are called as a simple sigma donors. Any example of it? Amine, aqua, pyridine, all these are simple sigma donors. They just donate sigma only. They just donate sigma only. Pi bases or pi donors, though we call it as a pi donor or a pi base, first of all sigma bond will be established. Definitely a sigma bond will be there. One pair of electron will be donated. After that, secondary interaction, based on that we are giving the naming. So the secondary interaction is, first it is giving it sigma. It is also giving another electron density, another electron pair. So it is like a double donation from the ligand. It is a double donation from the ligand. You can take all halides, OH minus. All these come under pi bases. They donate, double donate. They double donate. Pi acceptors, the name itself tells, any ligand has to donate a pair of electron to establish a sigma bond. Along with that sigma bond, either it can double donate or it can accept. In this case, it is establishing a sigma bond, but it is accepting electron density from the metal. It is accepting electron density from the metal. You call it as, what bonds do you call it as? Here I am writing them. That sigma bond, you call it as a dative bond or a coordinate covalent bond. And this pi bond, you call it as a retrodative bond, or you call it as a back bond, simply back bond, but it is called as a retrodative bond. So based on orbital overlapping interactions, ligands are classified into sigma bases. Since it is donating its sigma, you call it as a sigma donor. Pi bases, it is always donating a sigma, along with which it is also donating a pi. Pi acids, it is donating a sigma, but at the same time it is also accepting from the metal. So if it has to accept from the metal, such a ligand should have vacant pi orbitals in it. Only if it has vacant orbitals and metal is having a filled shell, only then such a thing will happen, or else it will not happen. If I choose carbonyl, carbonyl will have a vacant orbital. It will definitely have a vacant orbital. So due to that vacant orbital only acceptance will occur. If there is no vacant orbital, pi acidity will not have its existence. Suppose if I want to correlate this classification with the previous one. Previous one was moderate, strong and weak. Which ligands are stronger in this means? Pi acids are stronger because it is donating as well as it is accepting, due to which the difference of T2G and DG will increase, or what we call it as a, what do you call them as, HOMO and LUMO, or the frontier orbitals. So the gap will increase a lot whenever it is a pi acid. The gap between T2G and DG, if I am taking an example of octahedra, the gap between T2G and DG will increase a lot. That will happen only if it is a pi type of a ligand. That will depend on the orbital overlapping interactions. If it is a pi base which is double donating, the splitting will be very less. The splitting will be very less. It will not have a strength to split it to a longer extent. But if it is a sigma base, it can split to a moderate level. It is able to split to a moderate level that depends on T2G and EG level. That is the molecular orbital of octahedral. That is not there in your syllabus also. But just you have to understand one concept. Depending on the orbital overlapping interactions, suppose if it is a pi acid, since it is accepting into vacant orbitals, the energy levels will have a greater separation between T2G and EG. Such a ligand is found to be a more stronger ligand. Whereas if it is a pi base double donating, the separation between T2G and EG will be smaller. Hence you call all such ligands as weak ligands. Whereas sigma bases or sigma donors, they are moderate. Now if you are able to remember the spectrochemical series, according to crystal field theory, they have not given any basis for the spectrochemical series. They have simply classified the ligands, but there was no proper explanation. Now based on this, can you explain spectrochemical series? Spectrochemical series, if I start from the weakest to the strongest, the weakest will be halides. You might have seen it could be halides, OH minus and so on. So what are they? They are actually pi bases. Whatever weaker ligands that you see in the spectrochemical series, they are pi bases. As you come in between amine, ethylene diamine or water molecule, they are sigma bases. So all pi bases are weaker. As you come to the between of spectrochemical series, they will be sigma bases, and as you go to the end, most of them will be pi acids. Not all, most of them will be pi acids. CO, cyano, NO, or triphenyl phosphines, acetylene, or phenyl. All these are stronger. So this is one of the best classifications to explain spectrochemical series. Just a small classification which was made by Jorgensen. It is like a funny classification. All chemistry people are innocent. That is a general sense, because wherever I find all chemistry people, they are really innocent. So just like Jorgensen has also classified the ligands into two types. He called them as innocent ligand and non-innocent ligand. What is an innocent ligand? Simply I am giving you an example. If I give you a ligand called as fluorine, and suppose if the metal is combining with fluorine, what will be the oxidation state of metal? +1. It means if any ligand is allowing the oxidation state of the metal to be defined, such a ligand is called as innocent ligand. What is non-innocent? Name itself says it is non-innocent. It means suppose if I take NO, I am giving you metal. What is the oxidation state of metal? You can't say, because NO could be neutral, then this will be 0, or NO could be plus, then this will be -1. You can't predict. So such ligands you call them as non-innocent ligands. Or maybe I'll just put some metal and O2. Simply I put metal and O2. So should I understand this O2 as O taken 2? If I don't put parenthesis, should I understand it as O taken twice? Or should I take it as O2 or simply O2, dioxo? Or should I take it as O2 minus, or should I take it as O2 2 minus? Which one should I take? We can't say. So that is the reason such ligands are called as non-innocent ligands. Whenever your coordination complex has such ligands, it is difficult for you to calculate the oxidation state of the metal. So you have to be careful with such ligands. Okay? Write down the definition. First you note down the classification simply: innocent ligands and non-innocent ligands. A innocent ligand is the one, an innocent, you write an innocent ligand, an innocent ligand is the one which allows the oxidation state of the metal. An innocent ligand is the one which allows the oxidation state of the metal to be defined, which allows the oxidation state of the metal to be defined. Example, halides. Example, halides. Take an example of F minus. F minus. Next, a non-innocent ligand is the one which does not allow the oxidation state of the metal to be defined. Oxidation state of the metal to be defined. Example, NO, nitrosyl. It could be nitrosyl or it could be nitronium, we don't know. Example, NO, comma, O2. O2 could be superoxo, peroxo, dioxo, and so on. Based on bonding mode, ligands can be classified based on the bonding mode into two types. One type I am reclassifying again, terminal and bridging. Terminal and bridging. Suppose I am just putting it like this. It is like terminal. Bridging means this ligand is bridging two metals. Later on you have another type of classification called as end-on, edge-on, and side-on. End-on, edge-on, and side-on. I'll just take one example so that you will understand this. What is this end-on, edge-on, and side-on? I'm taking an example of dioxygen. As a ligand you call it as dioxygen. You should not call it as O2, you have to call it as dioxygen. Now for O2 or N2, such type of ligands, these are called as ends. One end, second end. These are called as sides. Okay? Suppose I am taking this. This is a side. This is another side. This is end. Side. And what is edge means this is edge. It is an edge. So suppose one side I have shown you. This is edge. So if the metal is coming and binding only this, you call it as end-on bonding mode. If the metal is coming and binding like this, side-on. It is side-on. Or if the metal is coming and binding like this, anywhere in the pi bond, then you call it as edge-on. End-on, edge-on, side-on. Again in this end-on, you have end-on terminal, end-on bridging. Bridging can be described by mu. Simply can give mu. If it is doubly bridging mu2, triply bridging mu3, quadruply bridging mu4, but simply bridging means mu. Edge-on, no further classification. Side-on, again terminal and bridging. So terminal, bridging, just I am drawing the diagram here above. Terminal and bridging. Suppose if I am taking a metal, this is metal and dioxygen. This is called as end-on because it is attached to a end. And only one metal is attached, therefore you call it as end-on terminal. For end-on bridging, I am drawing above. You can draw it below. For end-on bridging, this is end-on bridging. Both ends are now bound to the metals. So it is called as end-on bridging. Edge-on, just metal is attached to the bond present between the two oxygens. This is called as edge-on. Weak one. Side-on terminal or side-on bridging. I'm just drawing it above for side-on terminal. And for side-on bridging. If you are aware of this bonding mode, where do you find this type of bonding mode in bioinorganic chemistry? Bioinorganic. You find it in hemocyanin. Which bonding mode you find it in hemoglobin? Which bonding mode you will find it in hemoglobin? End-on terminal. You will find it end-on terminal for hemoglobin, whereas side-on bridging for hemocyanin. So all these bonding modes are important for us. Finish this classification. Last one you write based on denticity. Based on denticity. Denta means teeth. Teeth or tooth. So how many donor atoms are coming and binding means how many teeth are present or how many tooth are present around the metal. That is the meaning of denta. What is the denticity? Is it one tooth or many teeth? That is how you define. Monodentate. Another one has to be polydentate. Because based on this denticity only, we generally classify the ligands and will give it as monodentate ligand, monodentate negative, monodentate neutral, or bidentate negative, bidentate neutral, and so on. But this polydentate, we can further classify them into acyclic type and cyclic type. Cyclic type you can again classify into monocyclic and bicyclic. Monocyclic and bicyclic. So monodentate, polydentate is known to us, but again the polydentate can be classified into two types. One is called as acyclic and another one is called as a cyclic. In cyclic we have two different types, monocyclic and polycyclic. Monocyclic means simply we indicate like a cycle, somewhere you put a donor. It is just a general indication, not any ligand, just a general indication like there is a cycle and there are some donor atoms. Polycyclic means there is more than one cycle. Polycyclic means there are more than one cycles. Suppose if I just, okay, I'll just put this. I'll put this. Do you find any difference in this or not? How many rings are present? Then there is a difference definitely, right? Likewise, here also there is a difference. So here maybe this is the donor atom, this is the donor atom, this could be the donor atom. So there will be more than one cycle in it. There will be just more than one cycle. Any example for a monocyclic? A simple macrocycle. A macrocycle, that is the example. You can just draw a macrocycle below. I am drawing it here. Below that macrocycle you put an example of 18 crown 6. This is 18 crown 6. It is just one cycle only. Crown 6. Finished? These macrocycles are not there in your syllabus. They have just given you only chelating types, only chelate ligands. But what is a macrocycle means? One name I am giving you. It is 18 crown 6. How do you name them? 18 crown 6 means just count the number of atoms present in the ring. Count the number of donor atoms. The class name is a crown. It is just like a crown. Whenever you put a crown over the head, it is just like it will come and put it over the metal. Suppose if this is a metal, it will come and it will bind with the metal, just like a crown. So these are called as crowns or crown ethers. Whenever oxygen is present, you call it as crown ethers. So altogether, how many atoms are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. Altogether there are 18, in which 1, 2, 3, 4, 5, 6 are donors. So you name them as 18. The class name is crown. The number of donors are 6. Minimum there should be 9 atoms in a cycle, only then you can call it as a macrocycle, or else you cannot call it as a macrocycle. Okay? So any macrocyclic ligand should have a minimum of 9 atoms, out of which minimum must be 3 donor atoms. Then you can call it as a macrocycle. This has more than 9, this has more than 3. Therefore this is a macrocycle. This is called as 2-1-1 cryptand. You have more than one cycle. In this case, you have more than one cycle. Therefore, this comes under cryptand, cryptate ligands. So how do you number them? 2-1-1, or it could be 1-1-2, or it could be 1-2-1, but you have to name it as 2-1-1, the larger number, 2-1-1. Between the two nitrogens, one oxygen, two oxygens, one oxygen is present. So we are starting with the bigger number 2, 1 and 1. You call it as a 2-1-1 cryptand or a cryptate ligand. So it is just like if this is a macrocycle. Just imagine this is a macrocycle, just one cycle. A cryptand will be like this. If this is one nitrogen, this is a second nitrogen, one oxygen, two oxygens, two oxygens. So suppose if this is a cryptate ligand, a metal comes, this ligand can bind much strongly because it is like a ball. Macrocycle, it is just like a bangle or a circle, but these cryptate ligands are like 3-dimensional balls. So this will form a very strong bonds. These are called as football ligands. Cryptate ligands are called as football ligands. Okay, this is about cyclic. For acyclic also we have a classification. Is it done? For acyclic I am writing for acyclic there are 4 different types. One you call it as a linear, one is a branched, one is podal, P-O-D-A-L, podal. Fourth one is rigid aromatics. What is a linear ligand? Just suppose if this is a donor, it is connected like this. Just like a chain, it is connected. Branched, it is not like a simple chain, but it is like a branched one. N-alkane, isopropyl, so on. It is just like normal propane, iso, and so on. What is a podal ligand? Podal ligand means you will be having a base. Suppose if I am just drawing that base, from that base the donor atoms will hang. You will be having a base through which the donor atoms will hang. Such ligands you call it as podal ligand. And rigid aromatics means, suppose if I am just taking some aromatic rings, you can just take this as donor atoms. If I give you an example, you will understand much better. This is just a general description of that ligand. For a linear ligand, you can take an example of you may take ethylene diamine, or you may take, what is this, diethylene triamine, and so on. Triethylene tetramine, tetraethylene pentamine, and so on. This is a di-N. Di-N. Di-N means diethylene triamine. You can write down diethylene triamine. Di-N. It is also abbreviated as DETA. Diethylene triamine. DETA. Diethylene triamine. For branched EDTA is the best example. So we are aware of EDTA structure, 2 nitrogens through which 4 acetate groups are hanging. So it is like a branched one. EDTA is the best example. So it is not like a linear one, it is like a branched one. EDTA comes under a branched acyclic polydentate ligand. For branched. For podal, I am drawing the example for podal. Write down the ligand as tren, T-R-E-N, tren. Tren means triamino triethyl amine. Triamino triethyl amine. You can see nitrogen is present. From this nitrogen, one NH2, and another NH2. So if I am taking this nitrogen as a donor, from that nitrogen, 3 other nitrogen donors are hanging. So such ligand you call it as a podal ligand. Podal ligand. Tren means triamino triethyl amine. Triamino triethyl amine. One 1,3,5 triamino cyclohexane. What type of ligand is it? It is also a podal type of a ligand. There is a cyclohexane through which 3 amines are hanging. So if at all there is a metal, that metal can coordinate to the 3 nitrogens of this cyclohexane, and another cyclohexane will also come. It will again bind to the 3 more nitrogens. The coordination number will be 6. When you have 2 such ligands, coordination number will be 6, because this is a podal ligand, 3 nitrogens are hanging from it. This is a second example along with tren. For the rigid aromatics, the last example. For the rigid aromatics, take an example of OFEN. OFEN means orthophenanthrolene. OFEN means orthophenanthrolene. Orthophenanthrolene. If you have seen how did I write it carefully, you will understand the IUPAC importance. According to IUPAC, any stereo descriptor should be written in italics. whatever be the stereo descriptor, ortho, para, meta, cis, trans, all these are called as stereo descriptors, closo, nido, arachno, hypho, clado, etc. All such things should be written in italics only. You should not write it straight, you have to bend it. You call it as italics. Suppose I write do you find a difference? This we call it as italics. So any stereo descriptor must be written in italics only according to IUPAC. Second point, whenever you are abbreviating it, ortho is abbreviated as O, meta is abbreviated as M, para as P, facial, meridional, facial as FAC, meridional as MER. All those things should be written in small letters only. You should not write never capital letter. Capital letter should never be used according to IUPAC. So what is often means ortho. Ortho should be written in italics, small letter. Orthophenanthrolin. These are the donors. So this is like a rigid aromatic. It is not moving. It is a rigid aromatic. There is no single bond rotation type. Therefore it comes under rigid aromatics type. Orthophenanthrolin. Suppose if I am taking one orthophenanthrolin, it is giving you 2 donors, and metal may get 2 more such ligands. So if the coordination number has to be 6 for such a metal, how many OFN should I take? I have to take 3. Okay. So all these are different terminology of coordination compounds and coordination chemistry, along with the different types of classifications of the complexes we have chosen and classification of the ligands. So what are the different types of ligands, what are the denticity, whether it is negative or neutral, that we'll see in the next class. You can have a 10 minutes of break for the organic class to continue.